Okay, let's get started, people. Okay, so it's my pleasure today to introduce Sean Lovejoy on behalf of Bruno, who could not come this morning for a family emergency. So Sean Lovejoy got his bachelor and master at Trinity College in Cambridge, and his PhD in physics from McGill University in 1981. His work is primarily on macroweather with a focus on multifractality, and that can be shown by his two books published in 2015 and 2019 called The Weather and Climate, Emergent Laws and Multifractal Cascades, and Weather, Macroweather and the Climate, Our Random Yet Predictable Atmosphere. Sean is a faculty at McGill since 1985 and now a professor of physics. He's the founder of the joint AGU-EGU Nonlinear Process in Geophysics journal, and he's now going to talk to us about the future of climate modeling, weather details, macro-weather stochastics, or both. Take it away, John.
Good morning, and thank you very much for that kind introduction. Some of you may have heard me speak on various things over the last years. And I think it's been a little over 3 years. Just before the pandemic, I had a presentation. This one is going to be a bit different. So if you've seen the last one, it won't be a repeat, I hope. And the question that I want to focus on is how should we project the climate in 2030? I'll talk about a few other issues, but that's the main thing I want to focus on. And And the reason is going to become clear because we're now in a period of flux where there's a growing realization that something's got to give with the approach we've been following for so many years. So let me just back up a little bit to this World Modeling Summit for Climate Prediction, which was an international event held by the World Climate Research Program. There were something of the order of 100 participants, and many of them listed here wrote this up because they were in BAM's, Bulletin of the American Ecological Society, because essentially there was a consensus position that was adopted on quite a few issues. And so I'll come to what those issues are in a moment. Before I do that, just to mention that very similar conclusions were reiterated quite recently by the Royal Society in a briefing 2021 with, well, many authors, many of which are the same, in fact. The main, well, there were a couple of relatively small modifications, but one of them was, of course, the new urgency in 2021 to actually improve the projections, largely because the uncertainties at the moment are very big. So what were the main recommendations, if you like? First of all, exascale computing power was expected to be needed. In 2008, they talked about a 1,000 times faster computers. In the 2021, they talked about exascale, meaning 10 to the 18 flops. It turns out it's about the same thing in terms of power. So a lot of that would go to making finer and finer resolutions in the models. They both talked about kilometric scale resolution because they think at that level they might start being cloud resolving. Of course, clouds go much smaller than 1 kilometer, but anyway, we'll come back to that. The other thing they agreed on that there should be a huge, in fact, they compared this to CERN, the International Particle Accelerator in Geneva, that there should be some huge international institution created with a center. The 2021 recommendation was that, okay, it should be networked, so there might only be one big center in each continent, for instance. They nuanced this one big model. Is at the moment the uncertainty for the projections are obtained by looking at how the different models compared to each other, the spread of the models. So if you have one model, then you can no longer, at least it would have to be a rather different way of determining the uncertainty. So they admitted that there should be maybe a handful of models, whereas today there are probably 40 or more models that go into, say, the CMIP 6, the latest IPCC report. Okay, so those are what they basically agreed. And the final thing that they'd agreed upon is that the model should be seamless. That just means that you want, instead of having one model for doing weather predictions, another model for doing climate, you have a single model that you could just, ask it to do something at any scale. You want to know what's going to happen in an hour, you want to know what's going to happen in a century, you use the same model. Okay, that's the goal here. Okay, so I'm going to come back to that a little later. But the thing is, we had a rather disappointing decade that followed the summit in 2008. And what was that all about? So I want to just preface this with that it's really the evolution of computers, but coupled with the consequences for the climate sensitivity, which is kind of probably the single most important parameter when it comes to projecting the climate, right? So how many degrees of warming will you get if you double CO2, or essentially almost equivalently if you, if you increase the radiative forcing by 1 watt per square meter, how much does the temperature rise at equilibrium or balance? And so this is a plot here taken from Peter Lynch. And I've kind of extended it. He had two graphs here, two lines here. One is the evolution of the fastest computers at any given time. And the second one is the evolution of, so these are the different big numerical models that were used. So they show that they essentially follow, of course, this is a log plot, log flops against, log linear, log flops against the date. So this is an example of Moore's law. And you can see that, interestingly enough, possibly, ironically, like Richardson, Louis Fry Richardson, the person who essentially is the founder of numerical weather prediction back in the 1920s, he actually carried out a hand numerical integration back in 1920, pencil and paper, took him 6 weeks. And I kind of estimated that might be 10 to the minus 2 flops, 1 or 2 calculations per minute. He actually did these calculations to something like 12 significant figures or something. Anyway, but if that was true, then we'd had 66, in fact, doublings since then. Okay, that's a kind of more of an anecdote. The interesting points for us is the first GCM, basically, Manabian Weatherall in 1975, a couple of million flop. This is the kind of landmark U.S. National Academy of Science report in 1979. And these numbers here are the range if you double CO2. So 1.5 to 4.5, and it's become kind of iconic, but you can see the range is huge. The range is 3K or a factor of 3, depending on how you want to look at that. But a lot of uncertainty in what would be the amount. There's no question we'll get warming, but the question is how much. Okay, so the International Panel on Climate Change, IPCC, had their first report, assessment report 1 in 1990, and they came to essentially the same conclusion, 1.5 to 4.5 degrees. Computing speeds have gone up, and then AR2, the same thing. So computing speeds have gone up by already a factor of 10,000 or something. You can keep going, AR3, again, the same range. The AR4, slight change, 2.0 to 4.5, but almost the same range. And now AR5, I put here 1.9 to 4.5. Now this is actually the range of the multi-model ensemble 90% confidence interval. So AR5, the official range overall, taking into account expert judgment, was still 1.5 to 4.5, where it went back from 2.0 to 1.5. Okay, so until the AR6 came out in the summer of 2021, that was still the recommended range 1.5 to 4.5, but the GCMs themselves were 1.9 to 4.5. Now what happened in 2021, the GCMs, this is just the GCM range, 2 to 5.5. So it's actually increased. Okay, and before I go further in that, just note over this period, we've had an increase in computing speed, something like 10 to the 11. That's since the National Academy of Science. The other thing is algorithms have probably improved by 10 to the 6. That's an estimate by Peter Lynch. So if you take that all together, you get essentially 10 to the 17 improvement in performance. But in fact, what we're seeing is that the models are not actually, or the approach is not converging as it was hoped. So back to AR5, we had uncertainty range 1.9 to 4.5 for the CMIP. These are the models used the projections, whereas expert judgment was a bit wider. Okay, so but basically there was agreement. Not much difference here, and the actual median was pretty close. Now in the AR6, we found this bigger range for the GCMs, but the experts reduced their range by half, in fact, 1 to 1.5. So what does that mean? It means we need the experts more than ever, right? So the idea with all this is that the models would get bigger and bigger, and they would converge, and we could just throw away the expert opinion because that's fundamentally subjective, and we want to remain in a probabilistic, objective probabilistic kind of framework. So what's the explanation for the wider multi-model ensemble spread? I mean, wider means the results are more and more different from each other. 30 or 40 models that went into this. So the thing is that each team, since the previous iteration, 2013, each team has improved its model. They've used bigger computers, went to finer resolution. They've added in more processes. But when in doing so, they have made their model more different from the other guys who are doing exactly the same thing. So that's why the spread has actually increased. But at the same time, how the experts narrowed their range. The experts have narrowed their range because actually in the last years, there's been a lot of progress in improving historical estimates, basically instrumental over the last 150 years or more estimates. And also a lot more paleo data has come to bear on the problem. So the experts are much more convinced that the actual range should be 2.5 to 4. And so here we have a big disagreement now. Okay, final thing is that the regional projections. What about regional projections? Well, this is using the CMIP5 GCMs. Whoops. This was work with student there a few years ago. But what was done here was when one looked at the hind projections from the CMIP5 models, and we compared those with 5 different observational sets from 1880. And then you can compare, do the changes over that period. Okay, it's been normalized by the CO2 doubling. It's actually the transient climate sensitivity, but essentially it represents the change at that pixel over the period 1880 to 2016. So at the level of 2 standard deviations, the data and the projections disagree at the 95% level over all the regions where there's an X, which is something like half of the globe. So in other words, the warming patterns themselves are actually poorly represented. The other thing is that when you go from the present and project into the future, the models are essentially projecting linearly into the future. That's what these actually co-diagrams are similar to Taylor diagrams, but the idea is that, so you have all the members, say, of the CMIP5 MME here. This is their past average pattern, and then you correlate that with how they evolve into the future. Correlation 1 is on the outside of this circle, so they stay close to that, but the multi-model ensemble, the median is the black, and it's almost perfectly correlated. I guess 0.99 or something like that. And this is a low mitigation scenario, business as usual. But the point is that essentially they're linearly projecting in what they did in the past into the future, each model. So if they did a bad job in the past, don't expect them to do a better job in the future. Okay, so what was the response of the community to this? Because obviously people saw this coming before the AR6 report. So one of the responses is essentially to abandon quantitative projections. And this is the concept behind storylines, 2018 paper. You can see there are 19 authors, including some of the people who spent their entire careers building these models, right? So these are not just people from Mars that are coming down and saying, you know, I have a better idea, you guys did it all wrong. These are people who were participants, right? So their point of view is to be taken seriously. But what they say is a storyline is defined as a physically self-consistent unfolding of past events or plausible future events or pathways. No a priori probability of the storyline is assessed, and emphasis in place instead on understanding the driving factors involved and the plausibility of those factors. Okay, so that's what they mean by a storyline. What's the role of numerical models in the storyline? They are just tools to support and test theories regarding the interactions of climate processes, rather than as a source of quantitative climate predictions. And in fact, their goal is to replace objectively quantified probabilities with subjectively evaluated plausibilities. Ultimately, that's what they want to do, and they're quite upfront about it. So I consider that's a retreat from quantitative science to qualitative science. Another response is essentially black boxes. So black boxes can come in different flavors. There's artificial intelligence, neural networks. This is a pretty big group, 70 scientists from MIT, Caltech, JPL. They've got together in a group called CLIMA, but their aim is to reduce and quantify uncertainties in climate predictions, to exploit advances in machine learning and data assimilation, to learn from observation and from data generated on demand and targeted high-resolution simulations, for example, of clouds or ocean areas. So they're going to be staying with GCMs, but they're going to be trying to add AI on top of them to try and make them more efficient and more accurate. But of course, AI is a huge amount of parameters involved that are, you train them, you don't really understand what it's doing at the end of the day. A more radical proposal is this neural Earth system modeling proposal by a group of German scientists. So it's based on advances in neural networks and other deep learning techniques. And according to them, it should infuse Earth system modeling, but ultimately render them obsolete. And so they're more ambitious than just GCMs. Any Earth system model, they want to replace by neural networks. Okay, so what I want to argue today is that there's an interesting, promising alternative that I call a stochastic macro-weather alternative. In fact, I'm going to argue for a specific one of these, or specific flavor of these models is promising, but it's more that the basic outlines of what has to be done, I think we can more easily agree on. So, okay, so I'm just recalling that, physics is a hierarchy of different models and theories and paradigms, right? So you can start at a particle level, either classical or quantum. You have enough particles, then you want to treat that statistical mechanically. And for many purposes, such as weather and climate modeling, you don't actually care about the existence of molecules or not, because you're using continuum mechanics and thermodynamics, right? So the thing is that most of the details, where's the position and velocity of all the molecules in the atmosphere, those are just irrelevant details, right? And so the strength of continuum mechanics and thermodynamics is that they specifically ignore the things that aren't important and focus on temperature and pressure and macroscopic velocity and other quantities that we know about. Okay, so the fact that they don't acknowledge the existence of atoms is actually a strong point. The thing is, the hierarchy, of course, continues because the atmosphere is not just one vortex, and actually it's not even a collection of a small number of vortices. It's more like this spaghetti picture from a direct numerical simulation of your Stokes. So these are vortices, vortex tubes that are moving around like spaghetti, and they're being stretched by the dynamics, pinched by the viscosity, and evolving very complex. So but we have the same basic idea that most of the details of these vortices, where they are, how long they are not going to be important. It's the collective behavior of many large numbers that are important. So if we come back to the World Summit recommendations, so let me just give you a quick criticism then on the basis of what I'll be arguing in the next few minutes. So first of all, the exaflops are here, right, since June, although they haven't yet put the climate model into those computers. But the quantum leap doesn't see, well, it's certainly not there, and it hasn't materialized. The uncertainties are growing. Much bigger kilometric resolution. Why do you want to calculate details? 1 kilometer, the typical lifetime of a structure is about 15 minutes, right? And if your goal is to get a decadal projection of the temperature 2090 to 2100, you're going to be averaging that out by a factor of nearly 1 million. So what that means is you're going to be using the world's most powerful supercomputers, and in fact ones that don't quite exist yet, to essentially just average out. You'll be calculating a lot of irrelevant details, such as the fact that, according to the model in 2099, December 13th, there's a snowstorm in Montreal, and everyone knows there's no skill in that, but they're hoping that the decadal average over all that will be skillful, right? So, but if you don't want those details, you shouldn't be calculating them in the first place, okay? So if you do that, well, the huge international facility, maybe actually don't need supercomputers, although supercomputers are nice, but you can already do some interesting things just on laptops. In fact, as far as seamlessness goes, that's actually, in fact, going to be a disadvantage, right? Because there's a huge change in the property in the atmosphere that I'll discuss momentarily that occurs something around 10 days, the deterministic predictability limit. And we should be taking advantage of that rather than trying to model it in detail. So the basic ingredients that I think we need in a model, they should be stochastic, right? In any case, the GCMs beyond predictability limit become stochastic, so there should be no disagreement about that. We shouldn't be modeling irrelevant details. Of course, the problem is, what are the irrelevant details? So it's not as though it's a trivial question, but that should be our goal. We should be, in fact, so stochasticity ultimately implies that we're going to be trying to model the statistical consequences of the collective behavior of a huge number of interacting components. All of this becomes possible if you can exploit scale symmetry, so that statistically you can take into account relationships that exist between small and large, fast and slow. And another constraint is essentially energy balance that we know works, at least to some extent, because since 1968, we have Batigo and Sellers that gave us rather good average, say, latitudinal dependence of temperatures just by considering energy balance with the classical heat equation for transport. Okay, so let me give you some more argument for some of these ingredients. So we have scaling. So what is scaling? So specifically wide range scaling in space. This just shows spectra in all kinds of atmospheric fields. These are satellite fields. So log of the wave number spectrum is log of the wave number. So this is 20,000 kilometers, the size of the Earth, essentially. You have almost beautiful power law out to essentially the resolution, visible, infrared, near infrared, etc. You have the same for passive microwave, aircraft data up to 1,000 kilometers at least. Well, it goes further, in fact, and also reanalyses, and also, in fact, numerical models. Again, the size of the Earth. quite good scaling until some of the scaling is a little bit less good when you get to 5,000 kilometers and larger, but for below scales below that, it's quite good. So a power law relation. So what does that mean? So if the horizontal wind in particular is scaling, then one would expect there to be scaling in time. So what does that mean? It means that if you have something, this is a temperature, but a temperature fluctuation delta T that occurs over a time scale delta little t, then you have scaling, then that should go as a power of the lag. Turns out that actually this exponent here, so this is actually a relation between stochastic variables. If you want it, I mean, you could take ensemble averages and get it between average fluctuations. More generally, it will be between stochastic variables, and in multifractals, in fact, the exponent itself is a random variable, okay, with nonetheless well-defined statistics. But anyway, so this type of relationship actually is extremely general already. And what you see here is, though, that if you look at a fluctuation at a long time scale, lambda times longer, that's just the same as a short time scale fluctuation, but with the amplitude just modified by a factor. So essentially, if you have a range over which this type of behavior is valid, then you're essentially in a single dynamical regime, because qualitatively the fluctuations are the same over the range. So if you then take all kinds of data and look at the way this is actually the root mean square Haar fluctuation, but that's a technical aspect. But you can see that from, this is less than a second here, this is temperatures on the roof of the physics building. But you can do others, of course, then you have, this is actually, so this is now 10 days, you have temperatures, this is from some location in Wyoming, but so it's going to, the amplitude will depend on where you are locally. You've got here, this is the temperature fluctuations in Greenland, near where these ice cores that are shown in this plot over here. And here you have at very long time scales, essentially a biogeology regime, something like a million years and longer, Mesozoic. So basically, there are 5 regimes. The high frequency regime up to essentially the lifetime here of planetary structures, which is also almost the same as the deterministic predictability limit. That's the weather regime. Then, well, you could call the next regime after the 10 days or longer climate, but it's more logical, I think, to call the regime from now. So now we're in, there's a difference between industrial and pre-industrial, right? This is, if you like, showing the internal variability. If you average it out over longer timescales, you decrease the. So you take monthly, say, data, and you average it longer. Anomaly data, you average those anomalies, and the anomalies are converging to what you think is the climate, except that in the current epoch, right after about 15 years. Well, what's happening is the overall temperature of the Earth is going up, and so the place where the internal variability is converging you to actually then starts to move, depending on how much greenhouse gas basically that pumped in. But even if you go to pre-industrial from paleo data, you can see that you have the same kind of thing, except the transition where fluctuations start to increase is actually maybe more like a couple of centuries. But then it does increase up the Milankovitch scales. Okay, so I'm going to concentrate on this. The point is that the stochastic models basically model everything from this time scale onwards, Macroweather and onwards, whereas the GCMs are going to be starting, if we go down to 15 minutes, time scales that will be starting from somewhere around here, trying to get all this range, 15 minutes up to then 10 days, but then go past that. Okay, so what about energy balance? So, okay, so that is an argument that, there's this big transition, which essentially, for our purposes, what it means is that after something like 10 days, and it is variable, this is from latitude to latitude and place to place, there's a bit of variability, but it is typically 10 days. The ocean, as we'll see, is it's also turbulent, but with a transition time that's also variable, but more typically of the order of 6 months to a year. Okay, so but if we consider these timescales, then we can follow Bedico and Sellers, who started from essentially the heat equation, and they reduced it to 1D, which means 1D in space, meaning that it's the latitudinally average temperature they considered. And what they did was that, so they ignored the vertical, and they just said, okay, if at some location there's an imbalance in the radiative forcing, so obviously near the equator, you get more input than output in terms of solar and black body. The total radiative balance is positive energy coming in near the equator, and energy being more radiated to outer space near the poles. So what they did was they said, okay, let's just take all of that imbalance and redirect it towards the poles. So that was their approximation. What they could have done is to use, and what they should have done is to use the conductive radiative surface boundary conditions. They should have kept the 3D heat equation, but said, okay, if I have a forcing, so an imbalance, some of those watts per square meter are going to essentially increase the local temperature, which means you're going to have more black body radiation. So the linearized black body radiation for an anomalous temperature, surface temperature, is just Ts over the climate sensitivity. But some of that forcing will go into heating the subsurface. So sensible heat into the ground or into the ocean, depending on where you are. So that's the conductive radiative surface boundary condition. And if you do that, then, okay, let's see, try to take you through this rather simply. Let's just consider that the 1D situation. So Z is a vertical coordinate, right? So you have a thermal conductivity and a heat capacity. This is just a standard classical heat equation. And we could consider, let's say, what happens if you just put all of this forcing into heat. So you said all of the forcing just goes into the subsurface by heating. So it depends on the surface temperature gradient in its way. And the kind of, like I said, let's just take the square root of this equation. Well, very elegant. It turns out actually it can be put on a proper mathematical basis. In fact, using either Fourier techniques or Laplace techniques. This was done actually even in the 60s, but Oldham Spanier wrote an entire book about this, where essentially you get this half-order equation. So you get a half-order derivative by taking the square root of the normal equation here. Come to that in a moment. But they did this huge book. They were largely interested in problems in chemistry. They used different boundary conditions. But if you use the radiative conductive surface forcing, you get this equation, which is the half-order energy balance equation. Okay, so that's where it comes from. Whoops. So what's the fractional derivative? Well, the simplest thing is, of course, in Fourier domain, you're used to solving differential equations. You have a power d to some power, the differential operator to some power. Go to Fourier domain, it just becomes a multiplication by I omega, the frequency to some power. So right away, you can see that this is a power law, so it's scaling. If you write the same thing in real space, it's a convolution, of course, right? Multiplying by something in Fourier, a convolution in real space. And it's a convolution with a power law, looks like this. It's just a gamma function. And it turns out there are many fractional derivatives possible. The one that's relevant for us is the Weyl fractional derivative from minus infinity to t. But the thing is that what this means is that the half-order derivative, you put the little h as a half, you're going to get a very strong weighting on past temperatures. So past temperatures will have a huge influence on the way this term evolves in the future. We're going to come back to that. Okay, so we could move on to space-time regional Phoebe, Phoebe. So the Phoebe is the fractional, so it's actually the generalization H, little h is no longer a half. You've got the other term that comes in is it's essentially a divergence of horizontal heat flux. So what it means is you've got this term represents ultimately storage in the subsurface, and this represents essentially it's transport, it's the divergence of the heat flux in the horizontal, and you have this. So these are differential operators with 1/2 power. So it's a rather interesting mathematical problem. If you could specialize the PB into a latitudinal model to compare it to Bedico-Sellers. So Bedico-Sellers, the original 1.0 is this with H just 1, but if you put in this radiative conductive boundary condition, you get little h is a half. D then is the diffusivity at some location. Mu is the cosine of the cosine of the colatitude. Okay, so similar form, but a different exponent there. And you can see right away, okay, I don't have time to go through all kinds of evidence about this, but some simple things is if you look at the global temperatures, let's say, take the globally average temperature at 6-hour resolution from NCEP reanalyses, so it goes back about 70 years, you get a rather nice fit. This is the theoretical spectrum if you ignore anthropogenic. This data point here is essentially anthropogenic warming, but the rest of it is more or less just Gaussian internal variability forcing. Similarly, this is from paleo data, mostly pre-industrial, and so you can see the spectrum fits actually quite well back to about 1,000 years. Interesting thing is, if you look at the relaxation, so the relaxation time is the time that it takes essentially for equilibrium to be, or balance to be achieved. If you doubled CO2, how long would it take for balance to be achieved? Well, the answer is roughly the estimate is roughly the relaxation time. And the interesting thing is that the relaxation time is unbelievably variable from place to place. And in fact, this makes a lot of sense. So that over land, the blue here, it's going to be of the order of about a month or something, or 2 months, typically. But there are areas in the ocean where it appears to be literally millennia. So of course, these estimates were made with 70 or 80 years of data. So there's a lot of uncertainty there, but there's no question that there are some areas over the ocean, and these are the one right here with dark red, where you could have really, so it couldn't even be longer, corresponding to deep ocean currents. So it will take, that's how long it will take basically for equilibrium to occur over those regions if you double CO2. Okay, but a lot of the oceans are maybe more close to 1 year old. Okay. So that has the potential of answering various questions then actually about Milankovitch and what happened. Okay. So you can use, how do you use this for climate projections? Okay, this is work with student enrollment project. Right there. And so we use the Phoebe, we used past data, historical data. This is just global temperature average. We estimated from the past data H is about 0.38. We have this climate sensitivity. Remember the current expert range is 2.5 to 4, so it's more or less in there. The GCM range is 2 to 5.5, so it's a little low. These are the scenarios from the assessment report. So the 2.6 is a kind of high mitigation, 4.5 is some intermediate, 8.5 is the business as usual. You can compare, so the red is 5 actual historical series. So you have the historical, you have the Hein projection. This is the multi-model ensemble median in black. And you have the Phoebe median, or it's actually the mean ensemble mean, it's the blue. And you can see that in this period, this so-called the hiatus or pause period, where the GCMs were a little high, actually the Phoebe was more on the low side, but did probably a slightly better job. If you look at, this is just this moderate mitigation scenario to the year 2100, you can see that this is the 90% confidence for the model ensemble, with the middle here is the median. But you can see that the Phoebe has almost totally overlapping uncertainty limits. So essentially the models are virtually in complete agreement, but so models are basically in complete agreement, so they support. That means that models that are in fact have totally different, one of them, the uncertainty in the GCMs comes from what they call structural uncertainties, because the GCMs are different from each other, whereas the Phoebe uncertainty is parametric uncertainty, right? It's because the data is poor quality, or the model is not the perfect model for the real world. So it's parametric uncertainty. The median is something like 10 or 15%. So the middle here to the black there, it's something like 10 or 15% smaller. So it's not much difference. And the reason for that, by the way, is that according to our analysis, the aerosols were a bit too strong in the past. And so if you weaken the past aerosols in the CMIP 5 forcing scenarios, then the models have to become more sensitive to greenhouse gases in order to compensate. And then when you project into the future, you essentially, assuming everybody's cleaning up their coal-fired power plants or whatever, so less aerosols, and hence you end up with this. Anyway, that's the main source of the risk freedom of the median. But the most important thing is the uncertainty is much, much smaller. Okay, here's just a quick, this is just a regional projection, but this is an AR6, actually a high mitigation scenario, 2.6. So the overall levels are a bit smaller, precisely because of the aerosol thing. But basic patterns are not so different. But okay, so if you have two different approaches that both give you something reasonable, you can use one, or you can use them both as co-predictors to make an even better job. And this just shows, first of all, so here's the CMIP 5 multi-model ensemble in black. But if you take, this was a precursor model, but it's almost the same fact as the Phoebe. So what you can do is you can take each member of the multi-model ensemble and project it into the future using its own past, using this, and you can project it almost perfectly, right? So in fact, to project the GCMs over these scenarios, you can do it virtually linearly. This is the just doing the same procedure with the data. So instead of taking the past of the GCM, linearly projecting it into the future and finding that you get a good fit, you could actually take the data in the past and project that into the future, right? And that gives you the red line. And then you could take the best linear combination of the GCMs and the stochastic projection, and you get a hybrid, which is this thing, the blue line, the purple line there, which gives you even smaller uncertainties. Uncertainties, I didn't show them because it's a huge mess. The uncertainties on the basic models are the same as on the previous slide. Okay, finally, you can use the same idea to predict monthly and seasonal, make monthly and seasonal forecasts. I think I won't spend too long on this because you heard Simon Del Rio Amador, who notice is sitting back there, so he will correct me if I say anything stupid. But so he finished this about a year and a half ago, and still working on this latest part here, the hybrid part that I'll mention quickly. But the idea is that because you have this this half-order derivative, if you like, or fractional derivative, it represents a huge memory in the system. And that memory can be used to give you skill in forecasting. Okay, so that's the stochastics system. So these are all these acronyms here. CANSIPS is the Canadian Seasonal Interannual prediction system that's operated by Environment Canada. StochSIPS is the stochastics, seasonal internal prediction system that was developed by us years ago. And CanStock then is the hybrid combination of the two. And so, okay, so this is a slide given by Lennon, but the idea is, okay, so here's a 1 month beforehand, but maybe if you wanted to take it, this could be more informative here. So you have at this point in February 2007, you decide you wanted to make this is for globally average temperatures. These are anomalies, so the black shows the actual evolution of the anomalies over a year. The dark blue, the blue is the actual StochSIPS forecast, with the light blue being the 95% uncertainty band. And then you've got for the CanSIPS GCMs, you have all the different members of the dashed lines, with the median being the red line, and the median is the red line, and if you combine the median GCN is a bit below the black, and the StochSIPS is a bit above. If you combine them this hybrid way, you get the green CanStock, which is obviously much closer to the black, and you can do the same thing later. Maybe to see this in another way, what the hybrid does is it takes StochSIPS and gives it a weighting alpha, takes CanSIPS, gives it a weighting beta. So it's a linear combination of these predictors. So here you have it for essentially 0 month lead, K equals 1, 2 month, or 1 month lead, 2 month lead. And you can compare. Okay, so these are just the coefficients. So when you have red means that you've got a much stronger weighting, or you have a strong weighting. So, and when you have blue, that means that the CanSIPS is giving you most of the weighting. So the skill at a given point comes from CanSIPS, whereas say over here, over Brazil already, then StochSIPS is much more skillful. But as you move into the future, 2 months lead time, you can see that actually almost all of the globe, almost all the skill is coming from StochSIPS, with just the ocean parts from CanSIPS, and the ocean part in many areas are still in the deterministic predictability limit of the ocean model. So that there's no good explanation. You could look at a forecast. So this is the mean square skill score. So it's the fraction of the variance of the prediction. It's the variance of the error in the prediction divided by the variance in the anomaly predicting. So 1 is a perfect forecast, this could even be negative, in fact. So 0 is no skill. So you can see that to start with, so StochSIPS, you have some skill. Anyway, you can just compare StochSIPS minus CanSIPS. This means that the skill, if it's blue, that means CanSIPS skill is higher than the skill of StochSIPS. So first, CanSIPS is better over especially the oceans. But as you move into future, you can see once again that almost all the regions, in fact, the skill is mostly from StochSIPS. So there's a big potential there for hybrid. If you look globally, you see, so this is globally average, the skill over the pixels. So at 1 month, 0 month lead time, K is 1. Then you can see that so this is skill 15%, whereas CanSIPS has more like 35% at 1 month. But in 2 months, StochSIPS has got a higher skill than CanSIPS, and goes actually a bit negative, in fact, for CanSIPS. But in combination, the CanStock is in all cases, of course, better than either. And it's maybe, well, it's the same kind of thing. If you do it over land or over ocean, you break it up, this is the whole Earth, then you can see that actually over land, there's virtually no skill in CanSIPS after, for 1 month lead time. So there's quite a bit at 0 lead time. but then it actually becomes negative. Whereas stochastic and CMIP are about the same. Over ocean, there is still skill from basically the ocean part of the model up to something like 7 months, and it goes negative. But even then, the CAN-STOCH, the combination, the hybrid, is quite a bit better than both, in fact. Okay, so just conclusions just on that. So, okay, so we have, instead of an initial value problem, so the standard GCM is you start at t equals 0, you specify all the fields in the atmosphere, and then you integrate forward. The stochastics is a past value problem, so you have this long memory, and the more data from the past you have, the more accurate your result will be. So it's really a past value problem, mathematically speaking. And so you can, since they're totally different approaches, you can combine them, increase the skill from both. Okay, so combining them, this is the conclusions if you combine the two approaches. Okay, so you could still have, so even when CAN-SIPs and stochastics are both have low skills, combining them actually can give you quite a lot of skill, interestingly enough. And you could also, the whole theoretical framework about this could be expanded to other co-predictors if you like. All right, so one thing maybe you could do if you wanted, you could think of this, I mean, you could do it, think of it either way. If you like, you could think of stochastics as a kind of an advanced post-processing technique that will help you to improve the skill. And already, in fact, if you look at the way these long-range weather forecasts are made, is there's a huge amount of the effort is made is in correcting for known biases. So even half the computing time, in fact, now is getting huge. So you look at data mostly over the previous 5 years, and you correct known biases at each location. So it's a massive thing is to post-processing. Stochastics could be used, I think, more effectively because it realizes that 5 years it's currently used, say, the post-processing actually isn't really enough because the memory is really long, at least in many places, etc. Okay, some places it is enough. Okay, so the overall conclusions. So the AR6 report 2021 has revealed a crisis. I'm calling this, bigger is not better, but maybe that's the simplest way of summarizing the whole thing. Or bigger does not have to be better. It is in some cases. Basic thing is the CMIP 6 improvements drove the MME members further apart, and so the uncertainty range increased for the first time. At the same time, better historical paleo data means that the expert uncertainty range decreased. So alternatives are emerging, right? So this is being noticed by the community. So one is the storyline, which is basically you make qualitative and not quantitative projections. The other is black boxes, AI, neural network, okay, different mixes there. I'm proposing here that we should have an alternative that is fundamentally stochastic, that automatically then or potentially takes into account the collective behavior of many interacting components, and it tries to avoid calculating irrelevant details. We should use scaling, which is a scale symmetry principle, in fact, obeyed by the fundamental equations. So the GCMs are scaling, as I showed, but it's a mathematical property. And then we should use energy balance, essentially by updating the decosellers. So I think those are ingredients in what has to come next. I don't want to be, I have my own, this is my own pet. My pet here, candidate. You may not like this, you may want something else, but I think something else is needed. And of course, if you have something like that, then the hybrids seem to be better still. So we don't have to have all one or all the other. And as you know, for so many decades, essentially the only, the GCMs were, the only way if you wanted to get any funding in the field, you wanted to go forward, you had to say, well, yeah, if you give me $1 million, I'll give you something that will improve a GCM. Now I think there's an opening up to alternatives. And I think the time is right. So I'll stop there.
Thanks a lot for this really interesting talk. Do we have any questions? Dan?
You mentioned computational time. Does your stochastics, are they noticeably faster anyway?
Well, yeah, I mean, you make them on a laptop in Lennon is here. How long does it take you to do, let's say, a 6-month forecast at 1 degree?
The model role, it would take a few hours, but once the model is trained and you all know the ages of all the place, that makes sense. In a long time. So it's giving you less expensive computation. And I want to add on that so right now I finished all this production during my PhD, and now I'm working with that you can doing postdoc. But I've noticed that there is a huge field open to this alternative approach that maybe we don't know a lot about climate science. So we're used to make projections and to make predictions that are accurate. So we want to predict the short cycle, we try to deal with the best model in the short cycle. But in the industry, there's a huge field what they care about is not a given to the example what they want is actually to create all possible scenarios for the future. I cannot do that using usual DCF because we're bound to this computational cost. So if you want to project, I don't know, 1 million future scenarios of precipitation, temperature, flooding, tropical cycles into the future, I think that stochastic approaches are the best thing. Because you can just generate a million future scenarios like very fast, and you cannot do that using these things. So I think this is another advantage here. So for people interested in catastrophe modeling, insurance, financial, many people is so nothing climate. How do you translate climate into the real world? This is what they care about. How do you so use maybe kind of change. So they don't care about maybe there's going to hit 1.5 degrees in the future. They don't care about that. What they care about is at a given region, what are all possible scenarios of flooding or wildfire or tropical cycle that this is going to do. And I think stochastic approaches are a very useful tool. But that's not like an argument for the storyline. Yeah,
and stochasticity, I mean, sure, I agree. It's a way to parameterization, but you have to be very careful. I mean, with a lot of work adding stochastic forcing to models to get the spectrum, just the slope of the spectrum line, something as simple as that. But it's fake. You just do it until you get the right spectrum for the wrong reason, right? Or stochastic, for some. There's just different ways to do stochastic forcing. You mentioned twice. In fact, what you really had to do was get the resolution with the ratio, solve certain scales, and so forth. So it's not a one-size-fits-all solution. I think, but actually, I have a question that just sort of popped into my head while you were speaking. But as I understood your hybrid model, you run the GCMs, right, and then you run the updated Sellers model, right, and then you sort of take a linear sum of them to get something, right? Is that?
Yeah, you take the optimum linear combination of the predictors. Yeah.
So how do you find optimum?
Well, it's just I think it's the root mean square of the error. Or sorry, I guess in this case it would be. Sorry, how did? So yes, it's the root mean square in the past parts. Use the Hind projection to do that. Yeah.
But would it make sense to use the Sellers prediction as as something that you assimilate into the DCM. Like some sort of other hybrid where you're still treating the two very, very different.
Well, I mean, that hasn't been done as far as I know. I mean, but it could be done. But it seems that to a good degree of approximation with the scenarios that the IPCC scenarios. So you can have more extreme scenarios, of course, with the GCM. But the responses are pretty linear. That's the thing. And so they're regionally, they're linear in the sense that the patterns of warming are pretty much the same in the past and the future. And they're linear in the sense you can use essentially, this is a linear stochastic model to do a reasonable fit to each member and project each member using its past into the future. So in as much as we're nearly in a linear situation, then the best thing is to use a linear combination. But, the thing is the GCMs are indeed capable of tipping points. These will never give you a tipping point, obviously, right? No linear, that's a fundamentally nonlinear event. And nonlinear events, tipping points, unfortunately, may well occur. But at the moment, the GCMs in the scenarios that they have been used for, IPCC are not hitting points. So, anyway, so I'm not saying we should continue with the GCMs, but, maybe it depends, as you were pointing out, what is your goal, right? So
maybe, most applications combination will be you usually see and then
I know you want to follow up on this. Like, how far back in the past do you go when you use data for this like approach? Do you go LGM to now, or you go the last 100 years, or?
Well, for the climate projections, it was 1880, but for the forecast that the monthly and seasonal, I think it was 1948. You went back to with the NCEP reanalysis.
Use data to they have an hour of 5 and but at the end of the memory with the few uses now.
But I'm curious, like, let's say now we go back to we're in 1950 today, and you're making a projection. Like, how well would this approach do from scale climate change we had? Like, how far back do you have to? How much of the data from 1880 forward do you need?
Okay, well, that's a good question. Because you want to get the coefficients. Okay, well. Okay, so if you want to get the what's the optimum exponent and the climate sensitivity, so those are the key. And the relaxation time, those are the key model parameters, and then there's two other parameters to do with the one to do with the aerosols, one to do with volcanic, that needs to have some power taken in order to put it into a linear framework. So there's a total of actually 5 parameters. They are fit with a Bayesian approach. I don't think it would be too important if you cut off before 1948, because all the forcings are much smaller, except of course the volcanic could be bigger before. But if you just use the last 50 or 70, I think it would not
discard the last 50 years. We discard the last 50, only use 1880 to 1950.
Oh, okay. Well, the thing is, they're based on how much confidence do you have in the IPCC forcings when you go back, the earlier times. It's not clear, and but in the more recent times, you could have more confidence because so much of it is determined by basically greenhouse gases, which have actually been pretty well measured since the 1950s. But, so much of the forcing, I don't know, we can take it, we can see it right here. In 1957, I guess, was when you had the Mauna Loa observatories, you had this famous series. So that's around here, and the forcing is something like 0.1. So this is normalized by, this is the number of CO2 doublings, so it's 0.1 CO2 doublings. Now we're 2020, we're at like 0.6. So over that time, we've increased the effective forcing by a factor of 5 or 6 or something like that. So if there are errors of the order of 0.1, and that would be something like 0.3, 0.4 watts per square meter. If the errors are of that size, it's the huge error in the distant past before that, but it's not a huge error, for instance, now, right? So if we get various things wrong in the last couple of decades, it will affect the climate sensitivity, but it will have less of an impact than any previous time, right?
I think we have 2 more questions. Henry, you have a question?
Yeah, I think if you go to 2 slides forward, I just wanted to ask, and maybe you spoke about this, what exactly is it in the stochastic model which reduces the range in the predictions?
The uncertainty?
What is it specifically?
Well, okay, is it totally, okay, so we understand the source of the uncertainty for the multi-model ensemble, right? It's basically you compare all these different models and how close are they to each other ultimately. In this case, it's essentially parametric uncertainty. So what you have to do is you use the past data to fit the parameters, and there's going to be uncertainties in that, and those uncertainties then get propagated into the future, which is why, of course, they grow. The uncertainty in the projection grows.
Is it linear growth?
Well, the model it's fundamentally a linear model. Yeah.
So the uncertainties also grow.
So the uncertainties also grow as shown by the width of the blue lines here.
And we have 1 question online, so I'll read it. Sean and Lenin, I wondered if you could talk about some of the data you have used other than CMIP 5, CMIP 6 to estimate the FEBE parameters. Was anything ever determined with ERA 5 or similar database as you were once looking into? I recall that satellite data over reanalysis is preferred.
Yeah. So do you want to answer that, Lennon? Because you
the data we use for estimating
So if you use other data than CMIP 5 and CMIP 6 for the parameters of the FEBE, and if you use ERA 5 or similar database.
Yeah, for the FEBE, so for the system of prediction, we use reanalysis instead of ERA 5. But for the FEBE, I think it was based on observational data. So we have 5 observational data for global. But for regional, it was also reanalysis. This is acceptable.
Yeah, I hope that Julian heard you from the microphone. In case she can ask you directly.
So I think that you're arguing that we should use GCM's in combination with the stochastic models. But so I don't know if you've looked into this, but what happens if, so the advantage of the GCM is that you can assess nothing. So like, let's say you're interested in clouds and precipitation. Right? So let's say your stochastic model has smaller uncertainty, but then when you compare the GCM, which has, let's say, a similar uncertainty to the stochastic model, but or let's say it has a different surface and temperature prediction, right? But if you look at the processes of clouds and precipitation, and they match better with observations, like how do you reconcile that difference?
I'm not-
Processing.
So you're okay. So at the moment, we're only predicting and projecting the temperature. So the same framework could be used for precipitation or other variables, although the predictability is poor, and so we haven't tried projecting, say, precipitation. But I mean, even then, certainly the IPCC 5, they gave very low. They themselves evaluated that the skill of the precipitation projections were very low. I think they now have more confidence in the IPCC 6 precipitation projections, but those are notoriously poorly projected and predicted. And the same is true for the Phoebe model, at least from what we've seen in regional. So that's maybe not a good answer to your question, but because the GCM does more than one field, it does all the fields. Thing is, what is your aim? If is your aim to characterize the climate state, say in 2050, or or what? Because those details that you're talking about at small time scales, small space scales, what we need is something that will just give us the statistics of many of those processes, many of those events. So the only reason that if your goal is to get, a decadal projection, the only reason of calculating process, structures and things that live for 15 minutes is because you can't think of a better way of getting the statistics.
Well, of course, if you're interested in mechanism, dynamics,
Yeah.
there's all the way of going on.
Yeah.
It's like if you're using this GCMs, for example, and let's say that the GCMs are, like some GCMs are better matched with this. But however, let's say their clouds with precipitation are not, then how do you reconcile that difference then?
There are limitations to this model. One of the assumptions we have is kind of Gaussian. The first one is Gaussian. All the feeding comes from the heat concentration. So if you want to do all different processes, you can use technologies and balance model, right? So yeah, for example, if you want to so if you want to affect clouds in some region, we war that we're doing the solar right now. How is this going to affect climate in Africa? Cannot be that.
Well, I mean, you could try. I mean, there are techniques for synchronizing GCMs, right? So again, how can you use one GCM to help you improve another one? There's these nudging techniques, and I don't know very much about it, but I mean that exists, and it's a can of worms. I think I know. I had a long discussion with one of the people who was doing this quite a bit for the last few years, and it's very, very difficult to get two GCMs to talk to each other. So I don't think that it will be any different with a stochastic model. Different types. I don't think it will be any easier.
And you had a question, maybe it's the last one because we have already.
Yeah, maybe very short. I was just wondering, given this kind of your model is, as you said, you're running a laptop and it's much simpler in that way. And the goal is, let's say, you want to project the temperature multi-decade. I was wondering, thinking back about this black box approaches, let's say, this game, and interest, and even the capabilities that modern AIs seem to have. Do you think that the machine learning model would just be able to essentially learn this kind of equation relationship on its own, kind of this sufficient data, so that it basically would just say it comes out to be about the same, but perhaps this slightly different detail?
Possibly. I mean, because ultimately this is a linear. But this is a common thing in nonlinear processes, right? That you can approximate to some degree a nonlinear process, a chaotic system, by a stochastic process. It's linear even. And in fact, the question of whether the stochastic process should be linear or not, a nonlinear stochastic process, ultimately turns out to be a question of intermittency. So, and ultimately multifractality. If you want, so the thing is that in the atmosphere, strongly intermittent, most of the fluxes are concentrated in small regions of space. So you really need a multifractal stochastic model. And that, in fact, is a wide open question, right? I mean, there's very little work been done on that, but that would be the appropriate framework for directly making a stochastic model at weather scales. We're doing something that's much, much less ambitious, because it turns out that at these macro weather scales that the statistics are not that far from Gaussian. So the intermittency is very low when you take a monthly average anomaly set. Even if precipitation is not very high when you look at monthly anomalies, it's stronger, but it's so, you know, that's the region for the Gaussian approximation there.
There's also another problem with the machine learning methods. And as the method used for ground force, for example, to classify ground force to form models in the domain for the plan. But if you want to create the future, that goes out of that domain, and you cannot extrapolate this ground force. Maybe there are similar limitations if you do nets. So, yeah, you have to be very careful what the application will apply for. So, for climate change, ground force is a problem, neural nets would be a problem also. So at the end, you end up with maybe this linear regression, which is more or less the same outcome for the linear regression using data from the past. It's just that having these physical methods also is some kind of differentiation.
Okay, so let's wrap this up, and thanks again.
Some further questions?
Yeah, of course. I should. The only thing is, I have a Zoom meeting at 12:30, but
Okay.
I might be able to be a little bit late, but I can't spend a lot of time now.
Okay. Maybe just give you my question. If there's enough time, I can catch up later. Maybe you showed on a slide there is what you call regime change of the temperature fluctuation.